Now, there's just one last part to this, which is the last strategy. And we're going to essentially first give you the main concept of it. We call it discrete representation, and this has been an active area in the recent times as well. Now, the idea of discrete representation is to move away from real value vectors. Instead, what we're going to rely on are binary vectors. Now, why are binary vectors good? So it turns out that when you have binary code, it is very suitable for fast similarity search, because then you can define similarity in terms of the Hamming distance. So suppose that you have two binary codes, A and B. The Hamming distance between them is the number of bits that you will need to change in order to transform one string into another string. So in this case, you have A and B. So they are different in two of their bits. So in that case, their Hamming distance is 2. And this can be computed efficiently using the XOR operation. And because the XOR operates on the bit, is a bitwise operation, there are further ways to optimize for it. I mean, there are even hardware registers that can actually do XOR operations fast. Now, the idea then is to represent user and items in terms of binary codes. So instead of real valued vectors, we are going to rely on binary strings to represent a user and an item. Now, the advantage is that then it will be immediately compatible with retrieval schemes. One is called a Hamming ranking. Hamming ranking means that you don't actually use another index. All you do is still to do a linear scan, but this linear scan is going to be much faster for a couple of reasons. So one, linear scanning involves computing the similarity of the distance. But because now it's on fewer bits as well as in terms of fast XOR operation, each computation of the similarity is fast. Now, the second reason why this is also useful is because you also don't need to do sorting. Because for when you compare the Hamming distance between any two binary strings, the Hamming distance can go from 0 to the length of the binary code, which means that beforehand, the distances are also discrete, like 0, 1, 2, 3, 4, all the way to the binary length. Now, in that case, there is no need to do sorting, because then you can immediately place them in the correct distance functions. So you can just maintain a table where you say distance of 0, distance of 1, distance of 2, and so on, all the way to B. And you can keep, every time you measure the similarity or the distance, you can immediately put them in the right bins. So binning effectively can be done in constant time. And because of that, you can do retrieval in a very efficient way. Now, of course, you can also still do hash table lookup. In this case, you use the binary code as cells of the hash table, and then bin them separately in order for you to identify a smaller subset to compare to. Now, there is a difference between discrete representation that we're going to talk about now and the indexable representation that we talked about earlier. Now, in the case of indexable representation, firstly, we still learn real valued representation. Means they are pretty much still matrix factorization problems. You still get real valued vectors. You can do whatever you can do with the original matrix factorization vectors. Now, it's just that after that, you transform it into binary code using data independent hashing. So then you can just use any hashing function. Or if you don't want to, you don't even have to rely on binary codes. You can then use spatial trees or inverted index, and they're going to be generally applicable. Now, in the case of the discrete representation, it's going to learn binary code representations directly. So there is no further transformation, and that's essentially what you get at the end, which are binary codes. So there is a difference in terms of the perspective of how do we learn these representations. Now, we are going to cover maybe a small number of the representative work. There are others that they are based on similar ideas, but there may be some enhancements in terms of adding content and so on. Now, this is the basic idea for discrete representation. This is from a paper, KDD 2012. Now, the first thing is to represent every user and every item as a binary code. And for the purpose of simplicity here the binary code can either be -1 or 1. So instead of 0, 1, we're going to use -1 and 1. And it's going to be of length d, and we have to specify the length d beforehand. Now the prediction can then be measured in terms of the following function, which is a transformation of the Hamming distance, just to normalize it to between 0 and 1. So effectively, this particular function can be evaluated to 0 when xu and yi are completely different, and it's going to evaluate to 1 when xu and yi are completely the same. Okay? Now, for example, if xu are all -1s and yi are all 1s, so they are opposites, so in that case, this is going to evaluate to -half plus half, then it's going to be 0. But if they are all 1s, so 1s, you're going to get b over b, so this one is going to evaluate to half plus half is 1. So essentially it's just scaling to go from 0 to 1. Now, once we define this representation, the learning objective, if you look at it, essentially is the same as the original matrix factorization, which is still based on the prediction on the preference. It's just that now the prediction function is a different function than the original one. In fact, it still looks like it has an inner product component, except that the xu and the yi now are not real value vectors, they are binary vectors. Now, to do this is essentially going to be a difficult problem to solve, because now it's discrete optimization problem, and they are intractable, because we can't possibly go through all the possible combinations of binary codes. So one way to solve the problem, which is proposed in this KDD 2012 paper, is to have real valued relaxation. So meaning that we want binary codes, but we can't get them directly because it's expensive. So the way to do it then is to first relax the problem into real value problem, which is now you can find any real value between -1 to 1. Now, because it's between -1 to 1, eventually you get any continuous value in between. At the end of the process, once you learn the values, you need to round it up, you need to round it to binary code. And one way to round it, to make sure that the binning is not all going to go one bin, is that you can find the median value that is going to divide half of the items into one bin, the other half into another bin. Define that as a threshold, and anything less than threshold is going to be -1. Anything above that threshold is going to be 1. That achieve a particular balance between the codes so that you get more or less balanced binning. Now, this is one way of solving the problem. And later on, there is a follow-on work that appeared in CIR 2016 that argues that the real value relaxation is a problem. It's a problem because effectively you are learning two different stages. One, you're learning real value vectors, and then the second stage you are rounding them up. And because the rounding is independent of the real value solution that you get earlier, you might end up with roundings that are actually not suitable for the problem at hand. So the solution that they argue is, this is called discrete collaborative filtering, is to try to learn the binary codes directly. But learning the binary codes directly is still a very difficult problem, especially that, to improve the performance, they actually added a couple more constraints. So not only do they have to be binary vectors, now in order to achieve balance, we're going to make sure that if you take the binary codes and you multiply it by a matrix of all ones, you're going to get 0, which means that more or less you want half to be ones, half to be -1s. So you get a balanced partition. Now, we also want this to be decorrelated, because in that case, if you look at the covariance of the matrices, they're going to approach the identity function. Now, this is still a very difficult problem to solve. So essentially it's still intractable. They still need to produce another form of relaxation, except that now they don't relax the binary codes, they relax the constraints. So in this case, they define a real valued constraint, and we just try to approach that as closely as possible. Then through an alternative optimization scheme, where the earlier constraints are defined over the x and the y's, now is going to be defined in terms of some real valued vectors k and l, and we want to make sure that k and l are going to be as close as possible to the x as well as to the y. Now, and we just need to solve the k and l via SVD given some current state of the x and y, and once we have the real values, then we can try to satisfy this using discrete coordinate descent. Now, then to show that they do achieve much better performance for binary codes using this scheme. Now, this is for explicit feedback. So there also works in terms of implicit, which means based on the ranking. And this appears okay, so maybe we just look at a couple of results first. Now, MF is the original matrix factorization, meaning that these are real value vectors. DCF is binary code. This is what is being proposed in this paper. BCCF was the previous one that does the relaxation in terms of real values and then rounding. These are two other approaches that also does rounding. Now, what they are showing here is that if you look at the length of the binary code, 8 bits, 16 bits, 32, 64, as they increase the number of bits they need, they are already approaching the performance of the real valued vectors that you get from matrix factorization. So essentially, very similar level of performance, but in this case, because of the binary codes, they can get much more efficient retrieval. So, which is an advantage in itself. The top row here is based on the hash table, based on the Hamming ranking. The one below is based on the hash table lookup. Now, for the implicit feedback, now we're going to satisfy the ranking. But if you look at this, the formulation is very similar, except that now we want to make sure that if we see a triple, that user U prefers item I to item J. So in this case, we are going to satisfy this objective that makes sure that XUYI is going to be higher than XUYJ. But in this case, these are all binary codes. And they do show that if your objective is ranking, measured in terms of AUC, then the ranking-based approaches of implicit feedback is going to do better than the rating-based approaches that tries to fit the ratings. Now, these are essentially the key concepts behind discrete representation. There is just one last thing we would like to mention, which is there also works in terms of trying to absorb features. And one way to do that in matrix factorization or in a product sense is something called a factorization machine. That is where you have different feature vectors and you want to see the interaction across the features. And you can express this in terms of xi, xj, which are the features. And we're going to learn the vectors, the latent vectors, vi, vj, that is going to model the interaction between any two features. Now, you can also make it discretized by employing essentially discrete parameters instead of real valued parameters. And in that way, essentially you can generalize from the feature-based recommendation to that of discrete factorization machine. All right, I think let's summarize this here. So essentially, what we talk about here is a way to achieve discrete representation, which are going to be used for Hamming ranking and hash table lookup. Now, if we look at the objective in terms of the tree, so this is actually the takeaway from today's tutorial. I think we are looking at the problem of recommendation. And so far, a lot of the attention has been paid to the notion of accuracy, which is of course important. But at the same time, there are other concerns, and one of these concerns is the retrieval speed. And we are concerned with retrieval speed because in a way it's going to affect the user experience, because once we deliver the recommendations, we want this to be as fast as possible. Now, it turns out that a lot of the matrix factorization work that has been done in the past, it is certainly useful, and I think that's why it is so popular. But because it's not immediately compatible with existing indexing schemes out of the box, and that creates a certain gap that needs to be closed. And from the literature, we observed that there are essentially three main strategies to close that gap. So the first strategy is to approximate the maximum inner product search, which means that let's keep the recommendation algorithm as before, don't change them, just take one of them, and then we are going to employ some approximation in terms of the search based on those latent vectors that you get from existing recommendation algorithms. Now, the second strategy is to say that instead of changing the search function, let's keep the search function the same by employing existing indexing schemes. But in that case, then we have to change the recommendation algorithm so that it will then output a latent representation that is immediately indexable. Now, the third one, in a way, is a special case of the indexable representation. It's a special case because it focuses only on binary codes. And in that way, it achieves a certain level of compatibility with some of the indexing schemes, while in that sense, it may not work with some of the other indexing schemes like spatial trees and inverted index, but it probably does achieve the purpose of having fast retrieval as well.